Ladies and gentlemen, today we're going to tackle the dark sky paradox. Oh, and I got it on good authority that I'm right. I talked to this guy, yeah. Anyway, just kidding, I made this all up. Anyway, the dark sky paradox, I've been hearing about it for years, so I decided to look into it myself, and the solution is so easy. Anyway, let's give you a little background. So the dark sky paradox is saying if there are an infinite number of stars in the universe, then why isn't the sky blue at night? Here's the Milky Way. This is a 360-degree photograph. So these stars are actually behind us. These stars are behind us, and these are towards the center of the galaxy. So this is Andromeda. Look at all these stars in Andromeda. It's twice as big as the Milky Way. And if this were the Milky Way, we would be about let's see, we're about halfway between here and the edge. We would be about right in here, the Goldilocks zone. If you're in here, you're fried to death. If you're out here, there are no metals to make a nice habitable planet and biology. So this is the Goldilocks zone. This is about where we would be. Why does our galaxy look so dim? Well, dust. For one, the dust obscures the light. But that's not what we're going to get into today. What we're going to do, we're going to completely ignore dust. And we're going to prove to you why the sky is black at night. So let's say this is the sun right here. If you can imagine my drawing being a sphere. And this is the orbit of, say, Venus. And this is the orbit of Mars. Mars is about twice as far away as Venus. The surface area of a sphere is 4 pi r squared. And in this case, the r is twice as big for Mars as it is for Venus. So the surface area of the sphere is 4 times as much. You have to square the radius to get the surface area. And since the light comes out in all directions, it is lighting up the sphere relatively evenly, aside from any issues with the poles of the star. So it is lighting up the sphere evenly, and since the sphere is 4 times bigger, well, there's 1/4 as much light. So we have the Earth at 1 astronomical unit, 93 million miles from the Sun. This is the Sun in here. Venus is at 0.72, Mars is at 1.5, so Mars receives half as much light, or 1/4 as much light as Venus. But where's Jupiter? It's 5 astronomical units, 25 times less Sun. Saturn is 10 astronomical units. It's receiving 100 times less Sun. If you got into the sky at night, Venus looks like an airplane coming in for a landing. Jupiter looks fairly bright. It's pretty bright. It's not the brightest star, but it's pretty bright. And then Saturn is like, you wouldn't even know that it's a planet because it's dimmer than the vast majority of stars in the sky. Well, maybe not the majority, but it's dimmer than a lot of them. It's hard to tell which one's Saturn sometimes. And that's just 10 astronomical units. How about 20 astronomical units? That's Uranus, 400 times less Sun. Neptune, 30 astronomical units, 900 times less Sun, 1/2000th of a light year, 2.8 billion miles with a B, 100,000 million billion. That's just in our solar system. So what I've done, I've mapped the distance from the solar system. At this scale, the entire solar system out to Neptune fits in 0.08 millimeters. On this scale, 30 astronomical units is 30 inches. Here it's 0.08 millimeters. Where is the nearest star? Is it 1 light year? 2 light years? 3 light years? 4? It's 4.37 light years. How many tenths of a millimeter are in 30 inches? Well, I'll tell you, it's pretty small. If you divide 4.37 light years by 8.33 minutes, this is the distance to the Earth, the sun appears extremely bright because it's only 8.33 light minutes away. But 4.37 years divided by 8.33 minutes, 275,923. And you have to square that, remember? You have to square it. 76 billion times less sun. If the sun were here, it would appear 76 billion times less bright. Oh my God! So, how about all the stars in the Milky Way? Well, like I said, the sun's about halfway out. It's 26,000 light years. The Milky Way is 100,000 light years across. The middle of the galaxy is a big bulge like this, and has a bar here. It's called a barred spiral because the stars spiral out in these two arms, one here and one here, and then each arm splits in half, and then we end up with 4 total arms. But most of the stars are here, so I estimated that the average distance from the sun, or from the Earth rather, to all the stars in the galaxy is 35,000 light years, because this would be 74,000 light years to this edge. This would be probably like 67,000. This would be like 50,000. This would be 26,000. So even though it's vastly further away, the galaxy really thins out, and then it starts getting thicker and thicker, and then all of a sudden it's just so incredibly thick here. You need calculus to figure this out, but just looking at it you can say, well, it's about 35,000 light years. Besides, I asked this guy. He's been around. He told me. Nah, just kidding. Anyway, so the average distance to the star, all the stars in the Milky Way, approximately 35,000 light years. So we take 35,000 divided by 4.37 light years. We get 8,000 times further away. You square it, you get 64 million. 64 million. So how many stars are in visible stars? Well, we have 200 billion stars in the galaxy, and the nearest star is 76 billion times dimmer if it were the sun. So we have 200 billion visible stars. That's not counting red dwarfs, brown dwarfs, the ones you can't see. So we have to divide the 64 million by the 200 billion stars, because this factor is making it dimmer, but this factor is making it brighter. This fraction is about 2.64. So 64 million divided by 2.64 is 24 million. So the entire galaxy is approximately 24 million times dimmer than the sun. And here I did my fraction upside down. Sorry about that. So the entire galaxy is 24 million times dimmer than the sun. Now how about the next galaxy? Well, the next galaxy is the one I showed you, Andromeda. The Andromeda galaxy is 2.5 million light years away. Here's the Milky Way. It's 100,000 light years across. That's an inch. 25 inches later, we have the Andromeda galaxy. It's 200,000 light years across, or 2 inches. It's 2.5 million light years away. So if the average star in our galaxy is 35,000 light years away, and the average star in Andromeda is 2.5 million light years away, you have to divide 2.5 million by 35,000, and you get 71. And then you square that. 5,102. And then since Andromeda is 2 times as bright as the Milky Way, has twice as many stars, you take this 5,102, divide it in half, you get 2,550. So the Andromeda Galaxy is 2,500 times dimmer than the Milky Way. And I've been out at night looking for Andromeda many, many nights, and from the suburbs you cannot find it. You have to wait for a clear night, which is very once in a while. So yes, I can believe that this is 2,500 times dimmer than the Milky Way, because you can't even see it. Then you have to take the brightness of the Milky Way, which is 24 million times dimmer, again, multiply that by 2,500, and you get 61 billion times dimmer than the sun. The Andromeda Galaxy is 61 billion times dimmer than the sun. Here I did the math differently. I multiplied the 24 million by the factor of 5,000, and you get 122 billion, but it's twice as bright, so you cut that in half. 61 billion times dimmer than the sun. That's the Andromeda Galaxy. What about all the other galaxies? There are approximately 200 billion to 400 billion, depending on what year and what telescope we're looking at. More powerful telescopes get us a lot more. So we have 200 billion to 400 billion visible galaxies in the universe. Do those add up enough to make the sky blue at night? Well, if this is us, the Earth, and this is Andromeda, these are the galaxies in our local group. And if Andromeda is at 2.5 million light years away, the next big one, you know, it might be like 3.7, it might be like 4.5, 5, 10, 12, 14, you know, these are our local group. There's like maybe a dozen in our local group, and then there's a super cluster, well, then a cluster, then a super cluster, and then the galaxy goes out 13.7, what is it, trillion light years. 13.7 trillion light years. And we're talking 200 billion galaxies in the universe. And they're all spread out, not 2.5 million, but 13.7 trillion. That's a factor of, that's a million times 1,000 is a billion, times 1,000 is a trillion. So it's 2.5 million times a million times about 6 or 5, somewhere between 5 and say about 5.5. So it's like roughly 5.5 times a million squared. And that's the factor for the furthest galaxy away. It's a million squared, which is a trillion, times 5.5, so about 25 to 30, about 27.5. So the furthest galaxy away is 27 trillion times dimmer than Andromeda. 27 trillion times dimmer than Andromeda. It's a vanishing, if you're going to take the limit of an equation like 1 equals x squared, it just gets vanishingly smaller the further out you go. And I forget what the limit is as x goes into infinity. It's something like, I don't know, 2 or 10 or something. The area under this curve is a very, very small number. As the limit actually, I think this limit actually goes to 0. Yeah. Pretty sure this is 0. But the area under the curve is pretty small. And that's why the sky is dark at night. Because as you keep adding up galaxies, they don't add up. As you keep adding up stars, they do not add up. As you add up planets, they don't add up. They're just so far away. 30 astronomical units. 4.7 light years. 2.5 million light years. 13.7 trillion light years. Oh my G. Oh my God. All right. Thanks for listening. I hope this clears everything up.